Hello, my name is Bala. I am presenting my Adaptive Controls final project on control barrier function based adaptive control for human robot interaction. In this slide, you could see on the right a control barrier function based robot which is crossing a road network to reach its goal. On the left, you could see a control barrier function dividing the total state space state into a set of unsafe set and a safe set. Safety in human robot interaction is a really important aspect. We need to have the robots act in a very safe manner around humans. As you can see in the left image, the robot needs to be having a safe distance with respect to the human when it is trying to feed it. This is to ensure that the robot doesn't harm the human in any sort of unsafe manner. In a manufacturing setting, the robot needs to be within its workspace to ensure that the robot doesn't interfere with the human worker or also damage the human in any sort of unsafe and inappropriate manner. Safety critical systems are vital in dynamic environments, particularly in human robot interaction, where safety must be ensured. Adhering to stringent safety requirements is crucial in these scenarios to prevent potential harm. Control barrier functions are effective in formulating safety critical controllers that enforce safety systematically. Control barrier functions ensure that a system state remains within a safe set amid disturbances and uncertainties. This project focuses on developing an adaptive velocity controller using control barrier functions tailored for human robot interaction, in which we accommodate the specific challenge of maintaining a constant velocity while keeping a safe distance from the lead human vehicle. In our controller, you could see that the desired task or behavior is being fed into the nominal controller, which is then passed to a CVF based safety filter, which takes in the constraints and then gives out the control input, which acts on the dynamic system. In our problem statement, we take a scenario where the human maintains a constant speed and the robot is tasked with keep matching its speed and also maintaining a safe following distance from the human. In our case, the human maintains a speed of constant speed of VH and the robot aims to achieve a designated speed of VR while ensuring its safety. This safe distance S should not breach the safety constraint S is greater than or equal to T look times VR, where T look represents the look ahead time required to react appropriately to the human's movements. In our case, we develop a dynamic system using a dynamic interaction model where the equations of the motion are given by this set of equations, where VR, VH, and S are the robot's velocity, human's velocity, and the separation distance respectively. MR is the robot's mass, FT denotes the aerodynamic drag, AH is the human's acceleration, and U is the control input of the robot. We need to make sure that the human robot interaction scenario constraints are imposed to ensure the safety of both the human and robot. We also need to make sure that we are able to achieve the given performance objectives. In order to do this, we take use of two concepts called control barrier function and control Lyapunov function. In a control barrier function, we define the dynamics of the system using the equation x dot equal to f plus g times u of t, where x is the state vector and the control input vector is u of t. We need to make sure that u of t is restricted within a safe set. For this, we define a safe set C, which is defined as x belonging to Rn, where h of x is greater than 0. H of x needs to be a continuously differentiable function. In this case, it is the control barrier function, which dictates the safety constraints of the system. The control barrier function ensures that the state x of t remains within the safe set C for all time t. This is achieved if the condition supremum of u L f, which is the light derivative of f, times b of x, which will be here in this case a control barrier function, plus Lg times b of x, which is the light derivative of g times b of x, times u, plus alpha times alpha h of x is greater than or equal to 0. Here, alpha times h of x is equal to gamma h of x, where gamma is a user-defined constant which needs to be a positive condition. The system dynamics are given In case of a control Lyapunov function, we use the same system dynamics x dot equal to f plus g of u. Here the control objective is to globally stabilize the system towards the equilibrium point x star equal to u while ensuring that x of t tends to 0 over time through the application of our control law. A positive definite continuous function v here is defined as the control Lyapunov function helps us in stabilizing our control law. The system is considered globally stabilizable if the inequalities alpha 1 times of norm of x is less than or equal to v of x, which is less than or equal to alpha 2 times norm of x. Here the infimum of v dot of x comma u needs to be less than or equal to minus alpha 3 times norm of x, where alpha 3 times norm of x is equal to lambda v of x, where lambda is a constant greater than 0. We need to find a feedback control law k of x, or in this case it will be u, which it can be appropriately gotten through the equation v dot times of x of u is equal to lf times v of x plus lg times v of x times u, which is less than or equal to minus lambda times v of x. This ensures stability of the system without any need for explicit construction of v of x. In our scenario, we set up the constraints in two manners. One is the safety constraint, which is essential to maintain a safe following distance. This would be a hard constraint where S is the separation distance and VR is the robot's velocity and TD is the desired time headway. Safety constraint function formulation is being done by using a control barrier function h of x, which is equal to S minus TD times VR. This is critical for defining the safe set C in the control barrier function. We define our performance objectives, which would be our soft constraints, by using our robot's velocity. In our case, limit t tends to infinity, Vr of t is equal to Vd. Control Lyapunov function is used here to minimize the velocity error, where V of x is equal to half times Vr minus Vh whole square. In order to solve this problem, we use a quadratic programming solver. We optimize the robot's control input using the QP approach to minimize the cost function, here given by u star is equal to argument minimum of u comma delta half u transpose hu plus fu with respect to the safety constraints, where delta is the slack variable to ensure the feasibility of our constraints. We could keep our slack variable low or high in order to ensure our constraints, which in this case would be the soft constraints will be the velocity constraint and the hard constraint would be our safety constraint. So hard constraint needs to be maintained over all time and soft constraints need to be maintained as time tends to infinity. The control Lyapunov function drives the derivative of the control Lyapunov function to be negative, aiding in velocity error reduction, where the control barrier function ensures safety by maintaining a safe distance derived by the function. We define the matrices F and H in a manner such that we could balance the control efforts against deviations from desired behavior. In this case, the desired behavior being maintaining a safe distance S and also trying to get to a specific velocity. Here you could see the simulation outputs of our result. As you can see, it started off with a pretty high velocity, and as time passes by, the velocity tends to stabilize. Whereas in the case of control input, it exhibits an initial significant adjustment, whereas followed by stabilization, which reflects the controller's response to rapidly align the robot state with safety and operational targets. Figure 4, I'm sorry. In this case, our simulation results show our distance to human driver. You could see that the distance to human driver reduces to a stable safe distance, which demonstrates our proper stabilization effect of our control barrier function. As time passes by, it reaches a desired effect of 25 meters. In our case, we also plotted the control barrier function and control Lyapunov function. As you know, the control barrier function needs to tend to 0 in order to make the safe distance go to a required safe distance, in this case being 25 meters. Whereas the control Lyapunov function starts off with a very low value and as time passes, it reaches the high value because it has reached the desired velocity of Vd. Our project introduced a novel framework for controlling safety critical systems in human robot interaction, where we integrate control barrier functions and control YAPNO function to ensure the forward invariance of safe sets and also manage our performance objectives effectively while guaranteeing safety and operational effectiveness. In the future, we'll expand this application to other dynamic human machine interaction domains, such as assistive robotics and advanced manufacturing, where we can aim to enhance safety and the operational efficacy in various scenarios. Thank you.